January 1801. A monk named Giuseppe Piazzi is cataloging stars from an observatory in Palermo when he notices a faint point of light that moves. He tracks it for 41 nights, writing down where it sits each evening, and then the object drifts into the glare of the sun and vanishes. So he is left with a problem that should sound uncomfortably familiar. He has a small pile of measurements. Every one of them is slightly wrong, because 18th century telescopes and tired human eyes were slightly wrong. And he needs to tell other astronomers where to aim their instruments in the autumn, when this thing should emerge from behind the sun, at a place in the sky nobody has ever looked. Here is the trap. Through a handful of noisy dots, you can draw an infinite number of curves. Not a few. Infinitely many. Every one of them passes acceptably close to the data he actually collected, and they all point at wildly different patches of sky months later. Piazzi's measurements do not select an orbit. They fence off a fog bank of candidate orbits, and somewhere in there is the real one. Hold on to that, because it is the whole problem of learning from data, dressed up in a telescope. Your data never picks the answer. Your data only narrows the field. Something else has to do the picking, and whatever that something is, you had better be able to say it out loud. The astronomer who did the picking was a 24-year-old named Carl Friedrich Gauss, and his answer was almost rude in its simplicity. Among all the candidate curves, take the one where the total of the squared misses is smallest. Measure how far your curve sits from each observation, square each of those gaps, add them up, and hunt for the curve that makes that single number as small as it can go. That is least squares. That is linear regression, in the only form that matters. And notice what has just happened, because it is the move that quietly built the entire field. An infinite search over shapes has been converted into the minimization of one number. You are no longer asking which curve is true. You are asking which curve is least sorry. Why squares, though? That deserves an honest answer rather than a shrug, because the choice is not sacred. You could add up the plain absolute distances instead, ignoring the sign. People do, and it has a real virtue. It does not care much about outliers. Squaring is savage about them. A gap of 10 contributes 100, while a gap of 1 contributes 1, so a single wild measurement can drag your whole line toward itself like a heavy weight on a bedsheet. Squares won for two reasons. First, they are smooth. Absolute distance has a sharp kink at the bottom, right where you most need to know which way is downhill, and that kink makes the arithmetic ugly. Squares curve gently everywhere, so the slope is always well defined. Second, there is a probability story. If your measurement errors are the ordinary bell-shaped kind, then the least squares curve is exactly the most likely one. Gauss proved that too, which is why the bell curve carries his name. So squares are a modeling assumption pretending to be a default. If your data has genuine outliers, a sensor that occasionally reports garbage, a price field where somebody typed an extra zero, least squares will believe the garbage with real enthusiasm, and that is on you, not on the mathematics. Let us get concrete, with numbers small enough to hold in your head. Say you are predicting monthly rent from apartment size, and you have 3 listings. 500 square feet at $1,000. 1,000 square feet at $1,800. 1,500 square feet at $2,600. Your model is a straight line. Rent equals some rate per square foot, times the size, plus a base amount. 2 knobs. The rate, and the base. Try a guess. $2 a foot, base of 0. That predicts 1,000, 2,000, 3,000. The misses are 0, minus 200, and minus 400. Square them an average, 0, 40,000, 160,000, divided by 3, about 66,000. Now try $1.60 a foot with a base of 200. Predictions, 1,000, 1,800, 2,600. Every single one lands exactly on the data. Average squared miss, 0. That second line is not merely nicer to look at. It is measurably, numerically better, and it is better in a way you can compute without an opinion. That number, the average of the squared misses, is the loss. And once you have it, something beautiful becomes available. Imagine a landscape where east-west is the rate knob and north-south is the base knob, and the altitude at every point is the loss you would suffer with those settings. Bad settings sit high on the slopes. Good settings sit low. The best line in the world is the single lowest point in that valley. You are now standing somewhere on that hillside in thick fog, and you want the bottom. Gradient descent is the answer a hiker would give. You cannot see the valley floor. But you can feel the ground under your feet, and the ground tells you which direction is steepest uphill. So face the opposite way, take a modest step, and feel again. Repeat. The gradient is exactly that local sense of tilt one number for each knob, saying how much the loss would rise if you nudged that knob upward. Subtract a fraction of it from every knob, and you have descended. Run one step by hand, because the arithmetic is smaller than people expect. Start at the worst possible ignorance, rate 0, base 0. Your line predicts 0 rent for every apartment, and the misses are enormous, minus 1,000, minus 1,800, minus 2,600. The slope with respect to the base knob is just the average miss, doubled. Your predictions are far too low across the board, so the tilt says raise the base. The slope with respect to the rate knob is the average of each miss multiplied by that apartment's size, and because the biggest apartment has the biggest shortfall, the large size term dominates and screams raise the rate. Both knobs get pushed up, the bigger one harder. Take the step. Predictions rise. The loss falls. Feel again. That is it. That is the algorithm behind almost everything in modern machine learning, and it fits in one sentence: measure your misfit, ask which way makes it worse, and go the other way. The one dial that decides whether this works is the step size, the learning rate. Set it tiny, say 1,000th, and you converge, but you take 10,000 steps to travel a distance you could have crossed in 50. Set it too big and something more interesting happens: you overshoot the bottom, land on the far wall higher than you started, feel an even steeper slope there, and take an even bigger leap back. The loss does not creep down. It explodes, and in a few dozen iterations your parameters are infinity. Anyone who has watched a training run produce not a number has met this personally. Now the part that changes the shape of this whole story. For the rent problem, and for linear regression in general, you do not need gradient descent at all. There is an exact formula. Gauss had it in 1809. Stack your data into a matrix, do a specific multiplication, invert the result, and out drops the perfect answer, the true bottom of the valley, no stepping, no learning rate, no fog. It is called the normal equations, and it is one line of code. So why does every course on earth teach you to walk downhill on a problem that has a closed-form solution? Because the exact answer is the fragile one. Inverting that matrix costs roughly the cube of the number of features. At 10 features, free. At 10,000 features, an ordinary text model, you are inverting a 10,000 square matrix, and the cost has grown by a factor of 1 billion. Worse, the formula wants every row of your data in memory simultaneously. With 100 million rows, that conversation is over before it starts. And the deepest limitation is not about size at all. The closed form exists only because the model is a straight line. Add one nonlinearity, stack 2 layers, and there is no formula. None. Nobody is hiding it from you. Gradient descent survives all 3. It never inverts anything. It can look at 1,000 rows at a time and throw them away. And it does not care what is between your knobs and your predictions, as long as you can compute a slope through it. So the lesson inverts. You are not learning a clever way to fit a line. You are learning the only method that still stands up when the line becomes 170 billion parameters, and the line is the toy problem where you can check its work against a known truth. Which brings the fog back, in a form that bites people in production. Suppose you add a second feature, number of bedrooms. Size ranges from 500 to 3,000. Bedrooms range from 1 to 5. Those two knobs now live on completely different scales, and the loss valley is no longer a friendly bowl. It is a long, narrow ravine, steep as a wall across the bedroom's direction, nearly flat along the size direction. Gradient descent in a ravine is painful to watch. The step size big enough to make progress along the flat floor is far too big for the steep walls, so the path ricochets from wall to wall, crawling forward a sliver at a time. The fix is unglamorous and enormously effective. Rescale your features so they occupy comparable ranges. Divide size by 1,000. Center both around 0. The ravine relaxes into a bowl and the same algorithm that was thrashing now converges in a handful of steps. Nothing changed about the model. You changed the shape of the landscape it walks on. If you are wondering why anyone would compute the slope from a random 1,000 rows instead of all 100 million, that is worth sitting with, because the answer is not only speed. The small batch estimate is noisy, and the noise is a feature. It rattles you out of flat spots and shallow dips that a perfectly precise gradient would settle into and never leave. And that hints at the honest caveat. The rent valley is convex, one bottom, and gradient descent is guaranteed to find it. A deep network's landscape is emphatically not. It has ridges, plateaus, and countless local dips, and there is no theorem promising you the best one. It works anyway, spectacularly, for reasons the field is still arguing about. So when someone tells you neural network training is well understood, notice that we cannot even promise it finds the right answer to a problem we can define completely. The second thing worth sitting with: what would you actually check to tell a converged model apart from one that has quietly stalled on a plateau? 3 things to carry, then. First, data alone never picks a model. You pick, by declaring what counts as a miss, and squaring the misses is a decision with consequences for outliers, not a law of nature. Then, gradient descent is nothing more than feeling the local tilt of a lost landscape and stepping the other way, with the step size deciding whether you crawl, converge, or detonate. And the part that matters most, the exact solution to linear regression exists and is useless at scale, which is why the approximate, patient, downhill method is the one that ended up running everything. As for Piazzi's vanished object, Gauss took those 41 noisy nights, ran his least squares fit, and published a prediction for where the thing would reappear. On the last night of 1801, Franz von Zach pointed a telescope at that patch of sky and found it, the first asteroid, Ceres, recovered from a curve that was never observed, only inferred. The dots did not contain the orbit. What contained the orbit was a definition of regret, and the willingness to keep walking downhill until nothing was left to regret.